Well, here we are at the very end of Chem 140. And I'm just going to let this track play out because, I mean, the title of it is literally called Chill. We can become one with the universe. That was great. There we go. Okay. We have tracks from Undertale for today because the last day deserves the best songs. And if you don't like the soundtrack for Undertale, what is wrong with you? Welcome back to Chem 140. We're going to finish up Unit 16. There's like 4 slides left with some practice examples that I just want you guys to have seen and have these recorded so that you can review them before the exam and the final. On the screen is the problem that we did yesterday. We're also going to do Lab Worksheet number 5 after this, because Lab Worksheet number 5 is literally the application of what we're doing on the screen here. In fact, Lab Worksheet number 5 involves a technique called titration, and I'm speaking slowly because I'm getting my tablet out. I forgot to do that. But titration is basically how you get these numbers, where I don't have the pen selected. Where if I was reacting with a volume of substance, so like, oh, it took 27 milliliters of this molarity to react, I would get that by using a burette to titrate. And so our job in the lab is just going to be to see the technique and how it's done, and then see which numbers we use from that. When you say lab number 5, do you mean talk about it or actually do it? We're going to do a little both. Like, I'm going to walk you through the first bit for as much time as we can really put aside for it, because it's the last lab, right? And it's probably the most calculation intensive. And I sort of graded on effort. Like, if you attempted it and got answers that were sort of close, then that's fine when I grade it. Because I realized that you were studying for other things during finals week. And the lab sort of just falls here because it is literally the last thing we do in the class. So, all right. I'm going to give you a different reaction right here. So this is the neutralization of calcium hydroxide and nitric acid. And it turns out that when you react acids and hydroxides together, you get water as a result, and everything else just collects as the salt. So you're going to see this as a product for a lot of these reactions, because acid-base reactions are very simple titrations for us to study. So you're going to see water as a product a lot, and that's normal. Now, I'm not going to ask you to predict the products, but if, say, and this actually comes up on the worksheet, if there's a balanced equation that is necessary to solve it and they don't give you that, and you see that one is an acid and the other contains an hydroxide, one of the products will always be water. And then everything else is just the salt, and so you could figure that out from that. All right, let's suppose that I took this reaction and I reacted 15 milliliters of nitric acid, and the nitric acid had this molarity, completely with my calcium hydroxide, and it was 0.125 molar calcium hydroxide, and I put some random amount in. I don't know how much it was. What would that volume end up being? So solve for that. Since we did one of these yesterday, I want you to start by trying to do this on your own. You should be able to do it in about 5 or 6 minutes or so. Remember that your first move is to figure out how many moles of the thing that you were given both numbers for was. So you're going to start with this, nitric acid. Get to this spot here, and then work your way to the correct answer. Now, where do you start to get to moles A? I'm going to let you determine that. But it should be pretty straightforward based on the numbers that I underlined. So give it a shot, 5 or 6 minutes. We'll go over the answers when I get back. See you shortly. All right, 1 or 2 more minutes, and we'll go over the answer to this problem. All right, let's try and solve this. So if I push this here... Okay, we do need that equation on the screen, so I will leave that there. Let me... Oops, that's the wrong button. There we go. Okay. So where is my pen? It is always in a different spot. I have no organizational skills. All right, so since I am given a volume right here, I'm going to have to start by using that volume and the molarity to figure out the number of moles of nitric acid. So if I take the volume... Oops. I don't have the pen selected. That's not good. If I take the volume of nitric acid... Actually, you know what? Hold on. Let me just move this over here. There we go. Take the volume of nitric acid. I can then turn that into the number of moles of nitric acid. And then we just do stoichiometry from there. So moles of nitric acid would become moles of... What are we turning this into? Calcium hydroxide. And then we could find out what the volume of that is in a very straightforward manner. So let's do that. So we're going to start with the volume, which was 15 milliliters. Now, whenever we are working with molarity, we need to convert this to liters. So I'm going to do that without actually showing the calculation. Oops. Oh, man, I might have to reboot my computer again after this. But that's okay. So, again, you should know how to convert milliliters to liters by now. And so we'll turn volume into moles here. So liters and then moles, HNO3. And you might be thinking, oh, that looks like a molarity, right? Totally is. That's where we're going to fill that number in just a second. But we're going to fill in all the units first. So we'll turn moles of nitric acid into our calcium hydroxide using the balanced equation to put those coefficients in. And then finally, we'll do moles of calcium hydroxide to liters to figure out its volume. And this one is also a molarity. It's just upside down. And that's because we're dividing by the molarity. All right, let's go fill in all the numbers. And I'll just fill them in red. That's fine. So this is nitric acid's molarity. So let's find that on the screen. It's 0.225. So we'll write that down. Moles per liter. You don't need to put the 1 there. But you can if you want. Then in the middle, we have balanced chemical equation coefficients. So for nitric acid, there was a 2 in front of it, as you can see at the very top on that equation. And then calcium hydroxide had a 1 in front of it. So that's our equation coefficients right there. And then finally, I need the molarity of the calcium hydroxide, and that was 0.125 moles per liter. Make sure you're putting the correct number with the correct unit. So when you're putting it in a molarity, the number goes next to the moles, because it's moles per liter, not 0.125 liters per mole. That would be something different. And now that I have all of that information there, I can calculate it. Where did my calculator go even? There it is. My desk sounds a lot messier than it actually is. I'm just a scatterbrain. My desk is actually rather organized, and any normal person could find things relatively quickly, I imagine. All right, so when I did the calculation, I got 0.0135 liters, which we could then turn back into milliliters if desired. So to completely react with 15 milliliters of 0.225 molar nitric acid, I needed 13.5 milliliters of 0.125 molar calcium hydroxide. All right. Any questions, let me know. So we'll put all that on the screen here. There you go. All right, I do have one more problem on here. Actually, I think it's 2 problems here. So, using this balanced equation, what I want you to do is tell me what volume of 1.50 molar HCl will completely react with 52 grams of the solid iron 3 hydroxide. And then tell me how much FeCl3 will be made. That one I didn't specify what your unit should be, but because we don't know what the volume of the solution will be when the reaction is done, tell me how much FeCl3 will be made in grams. So that second problem is actually a unit 12 or 13. Now I'm getting the units mixed up. No, it's actually a unit like 15 problem. So we have already done all of that. And then the top problem, what volume would be used, is unit 16. So go ahead and try these 2 problems. This is great practice for the exam. And then once we're done with this, we're going to jump straight into the lab. So I'll be back in like 5 minutes or so. So see you in a bit. All right, about 1 or 2 more minutes, and we'll go over the answers here. All right, so let me clear this real quick. Boop. There we go. That works out pretty good. All right, so what volume of 1.5 molar HCl will react with 52 grams of iron 3 hydroxide? So we have a mass of FeOH3, which will turn into moles. Oops. And then since I want HCl, we'll turn that into moles of HCl. And then we can solve for a volume. So there's our blueprint for the first problem here. So we're going to start with our mass. And we'll turn that into moles. And we'll turn that into moles HCl. More or less just following this blueprint up at the top here, yeah? Which is what we've been doing all this quarter. Just convert one thing into another. Excuse me. That's the goal of 140, is convert everything into everything else, right? All right, so now we got to go look up these conversions. How do I convert grams to mole? We look that up on Lentech. I don't really need to put that up on the screen here. I got 106.87 grams per mole. Then I need the balanced chemical equation to figure out the relationship between moles of iron 3 hydroxide and moles of HCl. There's a 1 in front of iron 3 hydroxide in the equation at the very top there. And there is a 3 in front of the HCl. And then finally, what is the molarity of HCl? It is 1.50 moles per 1 liter. And we punch it all in the calculator. So let's see. 52, 3, 106.87 times 1.5. 0.973. Or 973 milliliters, which is a lot. All right, now let's do the second problem here. How much FeCl3 will be made in grams? And this is more or less the same type of problem here. We're going to stick with, I got to make sure I don't draw under this here, so. This first part is exactly the same. But then we'll go instead to moles of FeCl3. And finally, grams of FeCl3. And so this first part, which I'm going to copy from the top here, no different than before. So copy. Well, actually, you know what? You don't need that anymore up there, so I'll just drag it down here, right? So don't even need to paste. We'll just repurpose. Where is my, there we go. So we can convert from moles of iron 3 hydroxide to iron 3 chloride. And then for the last bit, we'll turn moles into grams. Just like we did in Unit 15. Now you can fill in the rest of the numbers. We already did the molar mass of iron 3 hydroxide. For FeCl3 and FeOH3, they both have 1s in front of them, so I'll do that. And then it's just how many grams are there in a mole of FeCl3. So I'll go back to Lentech. Type that in, and I got 162.20. So we'll type all of that in the calculator. And I got 78.9 grams of FeCl3. Sweet. All right. If you can do those calculations, you should be in great shape for exam number 2, because those types of calculations are really the hardest things that you're going to see on there. In fact, it might just be down to, can you do them quickly? So if you take 15 minutes to do this problem, that's too long. You have to do them a little more quickly. But if you can do this in 5 or 6 minutes, you're going to do fine. All right, so that is all that there is in my slides. So now we're going to switch over to, I might need a second window capture in here, but that's okay. To this guy, which is a little tiny. Let me make this bigger. So I don't know if I need the margins or not, so I'm going to just, we'll just do this for, oops. If I do, I'll make it bigger. I don't want to cut the chat out here. All right, so lab worksheet number 5 is basically everything that we did as a calculation today in a laboratory sort of situation. That was very British of me. In a laboratory sort of situation. So in the lab, what you are generally going to do is find solutions that are prepared for you. And then you will do the reactions that we prescribe in the lab protocol and determine quantities about them. So, for instance, we might have a solution that says 1.006 molar HCl, and then another solution that says unknown concentration of sodium hydroxide, and you might have to solve for that unknown. It's not really unknown. We know the answer. We just haven't told you. And that's the point of the exercise, is to do the lab technique and then figure out how to use that information you gather to do the calculation. Because it's literally just what we've been doing, with the extra step of now you have to find those numbers yourself by doing chemistry. So the first part involves what we did a little bit of yesterday. How do you make a solution? And the documentation talks about how you can mix things together. And we've already really talked about what this is, but what's important in the first part is, you can read this description later. It's not super important for right now. For the first part, we are going to be preparing the sodium hydroxide solution for the titration. So this lab is sort of two parts, and what we would do if we were actually meeting in person is I would have you do part A during the first week, and then part B where you do the titration in the second week. And so part A is, I'm going to make the solutions I will later titrate. And so this is the part where it's like, oh, I weigh out X number of grams, I put it in the flask that has whatever volume, I add water to the mark, and then I mix it really well, right? So that was just all the stuff that we did yesterday. And so that's straightforward. I give you sodium hydroxide, which is a solid, and I also give you a vinegar solution, which is a liquid, and it has a molarity. So for this vinegar part, we're going to include the dilution equation. And so that's what these directions are showing you. All right. We're going to talk about part B in just a second. We're going to go to part A. I'm going to show you what all of this means. So we're going to come back to this stuff a little bit later. So the pre-lab questions I'm going to have you do on your own, because you can do this by reading the directions here and then answering the questions. But there's always a lot of confusion on how to do these calculations, because I introduced this term dilution factor. What the heck does that mean? So we're going to do a few of these together. Oh, hold on, I need more water. Excuse me. All right, so we're going to start by doing question number 7. So we're going to go over here, and we don't need the PowerPoint anymore, so I got to figure out how to turn that off. There it is. What I do want is the PDF. Yeah, that's this one. Boop. That's not what I wanted at all. So how do I do this? Well, first I have to clear everything. All right, so our goal is to prepare that solution. 250 milliliters, 0.200 molar sodium hydroxide. However, I need to figure out how much sodium hydroxide I need to weigh out. How do I do that? I'm going to give you like 1 or 2 minutes to just think about this. You can try doing the calculation if you want. And then I'm going to do the answer in front of you, so everybody will have this answer. Okay? So go ahead and try this, because this is review. And I'll check back in with you in about 2 minutes, and we will do the problem together. So give it a shot. All right, so let's see if you have come up with the right answer. And you should get a very round number if you're still working on it. Now, I've given you a volume, and I've given you a molarity. What happens if we multiply those together? You get moles, specifically moles of sodium hydroxide. And then doing this step should be pretty straightforward, right? So I'm going to multiply these two together. Now remember, what do you need to do with your volume? Your volume must be in liters. Otherwise, multiplying it by your molarity doesn't get you an answer that makes any sense, right? So let's do that. So I've got 0.200 moles sodium hydroxide per liter times 250 milliliters, which is 0.250 liters. So that would be the number of moles of sodium hydroxide, since that's the only unit that's left anyway, right? So what I'm going to do is I'm just going to keep this calculation going. So now I'm going to turn this from moles into grams. So this will cancel out with that one, and I'll end up with grams as my answer. And I need to go look up the molar mass of sodium hydroxide. I believe it's 40. Yeah, 40.00 is what I have there. And so I have 40 times 0.2, which I believe is 4. No. It's 8. And then 8 times 0.250 is 2. So this should be 2. I'm going to put that in the calculator just to be sure. I'm trying to do that in my head. Nobody's impressed by my mental math. Yeah, it is 2. Look at that. Okay. So what I would always do in the class is I would have everybody do this calculation on their own, and then they had to show me their calculation, and then I would allow them to go weigh it. I'd give them a stamp on their lab book to say, you did it. And everybody's like, I got this really round number. And it turns out, yeah, it's kind of a weird circumstance, but you do get exactly 2 to 3 sig figs. And then your job is to go weigh out 2 grams of sodium hydroxide, and it comes in these giant-ass pebbles, and it's impossible to get 2. You just get as close as you can. All right, so if I was going to make this solution, I would need to put 2 grams of sodium hydroxide into a 250 milliliter flask. So that would look something like this. So here's my flask. And I'm going to put my little pebbles in here of sodium hydroxide. And then, if this is my fill line right here, I would add H2O to the mark so that I had, oops, overfilled it. So I would do this. There we go. You might wonder, wow, that's a very specific looking line that you drew for that. And so this is a part of the lab that a lot of students don't get to see hands-on without actually going in here. This is what's known as a meniscus. And so I'm going to zoom this in real big. So if this is my container, and this is the line that I'm filling, when you pour water into a narrow sort of tube, so like a capillary tube or something like that, what water does is water adheres to the sides in a way that defies gravity. Its ability to attach to the glass is stronger than the force of gravity or the force of cohesion between the molecules themselves. And so what you end up with is this curve called a meniscus. And a meniscus is a very awkward thing to have when you're trying to measure a volume. How do I get this on the line? And the answer is, well, we have to accept a standard. And that standard is that we want the bottom of the meniscus touches the line. Generally, you want the meniscus to rest on the line. Where in that line, because the line has a thickness, doesn't really matter. As long as the meniscus is in the line, and if you're just a little teeny bit below or above, that's okay. You don't want to be as below as this, so this would be too low. If you're too low, that's easy. You just add a little bit more water, and this level will go up. And so this is ideal. Right like that. That would be perfect. This would be great. That's not great. There, that's great. What would not be okay is if you did this. If you had too much water and you go over the meniscus, then your solution is no good. And the procedure for that is if you have too much water in there, you can't just take the water out. Can't grab a pipette or a eyedropper or whatever to just remove the water because it's not water anymore. Remember, it's got all this stuff in here and it's starting to dissolve, yeah? And some of it may have gotten up here. And if you remove the water, you're removing that too, and that's no good. So if you have too much water, the procedure is to dump it all out and start over. I'm not kidding. It seems really wasteful, and it is. So when you're preparing solutions, don't over add water, because if you go too far, you can't go back. And there's going to be a lot of that in this lab, it turns out. If you go too far, you cannot undo. You cannot Control Z in real life. Or if you use a Mac, whatever the hell it is that you do on a Mac. Flower Z? I don't know. So that's how we make a solution. You're going to add the solid in, add enough water so it hits the mark, and then, of course, the last step is to mix real well. Now, I suggest that you mix 50 times by inversion, which is you put a cap on the top, you seal it shut, and you flip the bottle over so that the water drains into the headspace, and that bubble of air that's in there shuffles around and it causes it to stir. And you do this about 50 times. People think, oh my god, 50 times? Are you serious? That's ridiculous. And really, mix it for about a minute. If you do that, you get a homogeneous solution. If you do it too little, then you risk not having a homogeneous solution. And that's no good, because we're going to use this later. Okay, so that's how you do the first part of your solution. So you've now prepared it, which means we've probably answered question 8, which I could just scroll by here, I guess. So. Oh no, question 8 is our dilution factor. So we're going to do this one together too. Now, unfortunately, I have to take up half the screen here because we need all those directions. But that's okay. All right. For question 8, what you are given is a vinegar solution. And the vinegar has this molarity. Now, it has that molarity because we have bought the vinegar from a supplier, and then we titrated it and found its concentration and wrote it on the bottle. Now, it turns out that concentration is too high. If you titrate with the sodium hydroxide that we just created, you would end up using more than 250 milliliters to do the titration because it's too concentrated. And there's really no reason that we need to give you concentrated vinegar for this because we'll just be wasting all of your solution. So what we do is we dilute it by a dilution factor. And so there's a bunch of terms down there that say dilution factor with a number 3, 5, 7, 10, or whatever. And so what we're going to do is we're going to apply the dilution factor to our original concentration to get a diluted solution. And its concentration will be less because we've diluted it, right? By what factor will it be less? And that is the number that is shown on the screen there, either 3, 5, 7, or 10. So we're going to do 3 as our example. So if I have a dilution factor of 3, here's the original concentration. And so if I have dilution factor of 3, then what I do is I divide this number by that factor. And that's the number that will be the new concentration that I want to make. So 0.8261 divided by 3, I get 0.2754 moles per liter. And so this is what will be our target dilution molarity. So for the solution with dilution factor 3, I want that solution to have a concentration of that amount. So in question 8, you are first determining the dilution factor and what the new molarity will be. And you do it like this. So you divide 0.8261 by the dilution factor. And so you get that. So that would be 3. So you should be able to do 5, 7, and 10 by just dividing 0.8261 by 5, and then divide 0.8261 by 7, and so on and so forth. And so you'd get those numbers. Then what we want to do is we want to make this solution. So now we're going to make this solution. And the way that we do that is, well, we have the stock solution right here. And this is going to be our diluted solution. So we're going to need the dilution formula. How do we figure this out? How do we figure out what we want? Well, we know what the molarity of the diluted solution is. That's this, because that was our target. We know what the molarity of the stock solution is. And you also know how much solution you want to make, the diluted volume. This will be 100 milliliters, because in the prompt up here, it asks you, make 100 milliliters. There it is. I've highlighted it for you. So now you just need to figure out what amount of stock vinegar you need to prepare this solution correctly. So let's do that calculation. All right. I do have to cover up the numbers, unfortunately. So let's take this equation. We're going to again solve for Vs because that's what we were doing all day yesterday. And so the dilute molarity is 0.2754. Oops, hold on, I forgot my unit. The dilute volume is 100 milliliters. And the stock molarity was 0.8261 moles per liter. These would cancel out. And when I do this, I get 33.33333. Oops. I don't know how to spell. So we would need 33.33 milliliters of stock solution to make the diluted vinegar solution with dilution factor 3. And then finally, we prepare the solution. So here's my flask. I'm going to add 33.33 milliliters of the concentrated vinegar, there we go. And then here's my fill line. We're going to add H2O to the mark. So we'll add the remainder will be water. Whoop. Meniscus touches the line. We mix it really well, and our solution is prepared. Okay, so that's part A of the lab, is doing those two tasks, making the solution of sodium hydroxide and making the solution of vinegar. So we're going to take a break. After the break, I want you to do the dilution factor 5 exercise. Okay, so starting from what we just did, instead of using a 3 here, use a 5. And so if you want to, you can do this during the break. But when we come back, I'll give you about 5 or 6 minutes to go over it. So we're going to do everything except instead of a 3 here, this is going to become a 5. Okay? And that's your job, is with a 5, change all of the prep and get the next answer. I'll give you a hint down here when you get your volume. Right here, you should get 20 milliliters as your answer, just to confirm. Okay? And then write out your procedure on how to make this in the chat. So we'll do that when we come back. So first we'll put up the break timer. It's the last break of the series of the quarter. This isn't a game show. All right, so I'll turn this on. We'll get the music going again, and I'll see you in about 10 minutes. All right, we're back. Oops, I clicked on the wrong thing. This is what I want. All right, so let's go over the solution for the 20 problem. Now, rather than me just change the numbers here, I'm just going to hit clear on this, and we'll just do it from scratch here. So, oh, since I hit clear, I can scroll all the way to the top, I guess. All right, so we still have our 0.8261 molar stock vinegar. And so we're going to dilution factor 5 this. And so that would be that. And I don't know what number that is, so we'll just punch that in the calculator. 0.1652. And so this is our diluted vinegar. Man, I don't know why my computer I don't know why Photoshop hates my computer. All I have played in the last 48 hours on this computer is Stardew Valley. It's not like I am overworking this computer. If you've played Stardew Valley, you know just how like graphically intensive that game isn't. So, I don't know, maybe my computer's just dying. I hope not. All right, so that's the diluted vinegar. So now we're going to take our equation. And I still want 100 milliliters of this. And the stock solution is still that number, and this is the dilute solution now. Now, something that nobody probably noticed, or maybe you did notice, but nobody has said anything, is, wait a second, when you did the calculation last time, you put this in milliliters. You didn't convert it to liters, did you, Wes? No, I didn't. And the reason for that is because if I was multiplying molarity times volume, my units would not cancel out, because if I did this, they don't cancel, right? But if my calculation is something like this, I don't need to cancel out the milliliters, and whatever volume unit I put in is whatever volume unit I get out. So for the dilution formula, it's okay to use milliliters for volume. And if you do that, you get milliliters out as your answer. So just be mindful of that when you are doing these calculations. If it makes you more comfortable and you don't really want to think, oh, do I need to do milliliters or liters for this? You just turn everything to liters and it's safe. But for the dilution formula, whatever volume unit you put in is the unit that you get out. So we'll punch all this in. So solving for VS again. And I realized that over there on my example, I flipped these guys, or the labels anyway, so this should be D. But it doesn't matter. The point is the same. And so the dilute vinegar was 0.1652 moles per liter. The volume I wanted to prepare was 100. Oops. Don't do that. Don't do 100 liters. That's way too much. If we had every student making 100-liter solutions, we would literally fill the entire room. All right, and then our molarity cancels out, and here you should get 20. And then for our preparation, we would take our 20 milliliters. Here's our flask. Here's 20 or so. I don't know, like that. Vinegar. I keep transposing the letters in vinegar. And then I would fill to the mark. So that the meniscus is right on the line there. And then mix well and enjoy. All right, so that's how you do part A of the lab. Any questions, let me know. You're going to do that again for 7 and 10, but in particular, the 5 one is the most important, and the reason for that is because later on in the experiment, we come back to solution B, which is the dilution factor 5. Okay, so you have described in your own words how to do that, so that's part of the lab assignment. So Kyle, you could just copy and paste that right into your lab. Don't copy and paste Kyle's, I will know. You might want to check the number of sig figs on your 20s, though, so just be careful. I realize that character limits and all. It's kind of important for that. All right, so for part B, we got to go back. Actually, what I'm going to do is I'm going to just scroll this right here, and then we'll go back over here. Part B, we're going to go back, and I'm going to show you a short video that I'm going to talk over. Hopefully the video works. Where is my video link? There should be a link of a person doing a titration. Do I not have one in this lab? I don't, apparently. Okay. Well, I will put this on the screen right here. And while I have that showing, I'm going to look for a video. So, YouTube. Titration. All right. Really, all I want to do is just show the technique here. So, okay. So, this looks like a student's video. So, we don't need audio for this. So, what I'll do is... How do I do this from here? Let's see. Yeah, let's do it here because I have one of these handy, so I could do this. And we can make it bigger. Oops, that's not bigger. That's still not bigger. Why are you like this, Google? Oh, because I'm holding the button down, because that was my fault. Okay. Alright, so on the screen, this student is going to perform a titration. Hopefully they're not going to, like, take the burette off of the stand and, like, I don't know, use it like a sword or something. So, alright, so I'm going to just point with my cursor here. Oh, okay. Alright, so here we got a bunch of equipment. So this is a pipette. The pipette is used to deliver fixed quantities of liquids into a container. And so, for instance, if I wanted to transfer 25 milliliters of one of those liquids, I could use the pipette to do that. And you can see the bulb on the end. And hopefully he's going to demonstrate that. Demonstrate the use of the pipette. We've also got a funnel. That'll come in use later. And then the burette is this attached thing over to the side. So what the objective is of a titration is to place a liquid that you are going to pour controlled amounts into the burette. Now, they have a really fancy burette that has a stopcock that's in that kind of a joint. That's uncommon right here. So this right here, this is uncommon. Generally speaking, there's like a little twisting dial that you spin it open, there's a hole in it and it lets the liquid through, and then you spin it shut to do that. So let's do this. Okay, so first they're going to prepare the burette. So you pour it in. like this. And you're going to pour one of the liquids in there. In our experiment, what we intend to go into the burette is the sodium hydroxide. So the NaOH is what is going to go into this. And that's what they're doing here too. Now, to prepare it, the way that you rinse it out is to add a little tiny bit of it and then let it drain through. And then you fill it up, but you don't fill it all the way up to 0. And I'm going to show you that in a second. Then the next goal is to take the other substance that you're going to analyze, and you're going to pipette that into a flask. And so that's what he's doing here. He's going to pipette some volume of the analyte here. They're using HCl, but we're going to be using sulfuric acid for the first part, and then vinegar for the second part. And we don't need to see him accurately measured in there. So that's where our analyte, the acid that we're going to measure or analyze, is going. And so he's letting that drain out. And then finally, before we start the titration, we need to add an indicator. There is an issue with doing chemistry for acids and bases, and that issue is they're both colorless compounds, and the only thing that really comes out of them when they react is heat. And heat is notoriously hard to measure quantitatively accurately. So, like, you could use temperature and stop measuring, or say the reaction is done when the temperature stops increasing, but other things make heat too. For example, just adding one of these things to water produces a little bit of heat. Molecules moving produces a little bit of heat. That's ambient temperature, right? What if the heater kicks on in the room? Like, there's all sorts of potentials for error. So we need something better than that. And the way that we do this is we add a visual indicator. The indicator used in an acid-base titration typically is phenolphthalein. And what phenolphthalein is it's a colorless substance that if you pour it into an acid, it stays colorless. But if you pour it into a base, which is what NaOH is, it turns bright, bright pink. And so you'll see this in a second when he does the titration. When the reaction is done, all of the acid will be neutralized, and you'll be adding more base to it because you're adding sodium hydroxide, which is the base. When there is more base than acid, the solution will turn pink and you're done. What that means is that all the acid is gone. You've reacted all of it. So you know what amount of base that you added reacts completely with the acid. All right. So this is just a close-up of the burette. And you can see here that the numbers count down as you go up the burette. So they increase as you go down the burette. That might seem kind of weird because normally we are used to containers having the volume printed on the side to show us what's in there. But a burette is different. A burette shows us how much you have used. So, for example, the burette currently says 33.40 milliliters, or whatever. And so what I'm going to do is I'm going to turn this off the screen real quick. And we're going to show just a little example of what's going on here. So if I have my burette, and we'll say that we'll just do every half. Or so. And it's right here. And I said that my number was 33.40 milliliters. I don't have the right number of sig figs for my marks, but that's okay. It's consistent with what the video is. When I open the valve down here, this will go down. And we'll say that it stops down here. And I close it again. So I started with this much volume registered. When I finished, I had this much volume. We'll just write that. How much was used? Well, it's wherever you ended minus wherever you started, right? So that would be 35.75 in this case minus 33.40. And I would subtract them. Oops, I lost my decimal point there. And this is the amount that you would have used. This is registered in the lab report as delta V, or the change in volume in the burette. So this is the volume that was used for the experiment. Okay? And the way that you get that from your burette is to measure the starting place and the ending place and subtract the two. You should get a positive number because you used a positive volume, right? You can't use a negative volume. That's not a thing that exists. So in the experiment, what I have done is I have done the experiment and given you some data tables here. There's my initial volume. There's my final volume. So you can see in trial 1, I started at 0.20. And when I was done, this is what it said, 15.78. So how much NaOH was used in the experiment? It would be the difference between those two, or 15.58, right? Once I know that amount, I then can do the calculations for stoichiometry based on what we've done. So that's really the technique part here, is how do I figure out what volume was used? Well, you're just going to subtract final minus initial, and you're going to report that result here. So we can do that on the screen. So for trial 1, the final volume and the initial volume was 15.78, and the initial was 0.20. So that's how much was used. All right. What was this? When you look in the data, you can see that this was sodium hydroxide. The next step that we're caring about is calculating the molarity of the sodium hydroxide. And the reason that we're doing this is because in this experiment, for the first part of part B, you are going to react sodium hydroxide and sulfuric acid. And you are going to use a known concentration and volume of sulfuric acid. So you know how much acid is in there in terms of its molarity and its volume, and therefore you know the number of moles. So now you can answer question number 11, right? So first, let's write the balanced equation for sodium hydroxide and sulfuric acid. So one of the products is always water for an acid base if you're reacting with hydroxide. And then the other reactant is just everything that's left over to make an ionic compound. Well, I've got sodiums and I've got sulfate. So I need to make a sodium sulfate. However, if you know what the charges are on these, those charges wouldn't balance out, right? So I actually need 2 of these. Now, how would you predict that? If we were actually going to go over examples here, I would have you write out all of the ions that form. And I'd say, okay, well, you need to add stuff so that you can make a balanced equation. It turns out if you do this, then here's my water, and then everything else is the salt. So we would do something like that if we had more time, but we don't cover net ionic equations in this class, so we're not going to worry about it. But that's the balanced equation for this reaction. You're going to have to make one similarly for vinegar, and you can always ask questions about that on the Discord if you need to. So there's our equation. 2 sodium hydroxide plus a sulfuric acid makes 2 water, and sodium sulfate. Next up, we're going to figure out which one of the things we know... Oh, I'm at the bottom of the paper, so we'll go all the way back up to the top here. Which things do we know so we can do the stoichiometry? So for the sodium hydroxide, I know that I use the volume shown in the reaction, right? I don't know its molarity, though. We presumably know what its molarity is because we made the sodium hydroxide, but because there might be error involved, we're going to solve for it instead. For the sulfuric acid, I have instructed you to use 25 milliliters and a molarity of that, 0.0750 moles per liter. So since this is the one that you know, both M and V, you can figure out the number of moles, right? And then if you know the moles of sodium sulfuric acid, you know the moles of NaOH using the balanced chemical equation that we just read at. And if you know the number of moles and you know the volume, you can then solve for this. So let's do that. All right, I'm going to shove this off the screen a little bit just so that we can have more space. All right. So for trial 1, what I would do is the following. So first we need to figure out the moles of H2SO4. And that would be, this is our concentration, and this is the volume that we used. And so I times those two together. So in this experiment, I put this many moles of sulfuric acid into the container. Okay. Now that I know the number of moles of sulfuric acid, I can take those moles of sulfuric acid and figure out how many moles of sodium hydroxide are needed, right? And we do that just like all those problems that we've been doing in Unit 16. So I go find the balanced chemical equation, and I've already erased it, but if you write it down, you should remember that there was 1 sulfuric acid per 2 sodium hydroxide. And you would get this as your answer. And then finally, we need to find the molarity of this. Well, molarity is just moles divided by liters, right? Well, here's our moles right here. What's our volume? Well, our volume is what we used up here. And so if I just divide those two numbers, moles divided by liters, I will get the molarity. So the moles was this many moles were reacted. And the volume for this experiment was, in liters, 1.5, I've already forgotten the number, 1.558. And so the number that I get when I do this calculation is 0.241. Wow, I don't know what I did there. There we go. So this is the concentration of sodium hydroxide that was actually prepared, as opposed to the 0.2, which we were trying to make earlier. Now, why is it off by so much? It's because the pebbles that are used for sodium hydroxide are very large, and it's very difficult to get exactly 2 grams. So it's very easy to go over. And I've purposely done so for this experiment. So that's how you do trial 1, if that was the only trial. Now, what you're going to do on the actual worksheet is, instead of using my number for trial 1, you're going to get the average volume instead, right here. So you're going to find out what volume of sodium hydroxide was used, take the average, and then use that number in the average box as your volume of sodium hydroxide. So your answer is going to be very similar to mine, because all the trials are roughly 15.5 milliliters, as you can see from the data here. But they're not exactly the same. So run through that calculation for the average volume in the lab, and you will get a result that's very close to what I just got for trial 1, okay? So instead of doing what I did and doing 3 complete calculations, just take the average NaOH volume and then use that to do the calculation we did. I didn't want to give you the exact number, because then otherwise I'm just basically doing the lab for you. But in doing that process, that will give you the answers to all the way up to number 14. For what it's worth, number 14, there's an error right here. There should be an enter. Oops, I tried to hit enter, but I couldn't. So this question ends, and then this statement right here is for everything past and below. Okay, so there should be a line right here, a gap. So this is all the first part of part B. The second part of part B is, okay, you have now figured out what the molarity of sodium hydroxide is, which you can put in the table. So this box right here should be your answer from problem 14. Or sorry, not 14. 13. So whatever you calculated the molarity to be from this first table, you're going to enter that right here. Because now, in the next problem for this table, your objective is to figure out the molarity of the vinegar, using the known molarity of sodium hydroxide, because you just solved for it, and the volumes of sodium hydroxide that you used in these experiments. And you'll notice that they're different. So taking the volume for this, multiplied by your molarity, will give you moles. And then you can do the same process, but figure it out for the vinegar. So let's do an example of that. We're going to shove this off the screen just a little bit. We'll come back to it in just a second. So instead of using the average volume, I am again going to use trial 1. So there's our molarity for the sodium hydroxide. So sodium hydroxide, we've calculated it to be this. For trial 1, the volume that I got was 18.06 minus 0.09. And that's 17.97. So I'm going to write that down. For that. On the screen, you can see that the vinegar we used 25 milliliters. But we don't know its molarity. So we're going to do this same process, except go in the other direction. Because if I multiply these two together, I get the moles of sodium hydroxide. I can then use a balanced chemical equation to figure out the moles of vinegar. I'm going to leave that exercise for you to do, but I'll just give you a hint. The ratio is 1 to 1. And then finally, we can figure out the molarity of vinegar. All right, so let's do that for the sodium hydroxide real quick. So 0.241 moles per liter, and I used 0.01797. That's not a 7. There you go. So that's how many moles of sodium hydroxide are in there. And then I told you the ratio was 1:1, so when you do this calculation, you just have that. So you get the same number out. And then finally, I now know the number of moles, and I know the volume of vinegar that was used. I can figure out the molarity. And so that would be this many moles of vinegar divided by the volume that was used. Oops, I don't get that 2 on the end there. Now, this was dilution factor 5 for our experiment. So part of the lab will tell you, okay, take your number that you just got and go compare it with the dilution factor 5 result that you got in problem 8. And how close are they? Calculate a percent error. For reference, the number that we got in that problem, so the dilution factor 5 should be, is it 0.8261? I can't remember. Just a second. Yeah, so the number I got for the dilution factor 5 was 0.1652 when I punched it in the calculator. And so that's pretty close to what we got. All right, that is the experiment. That is my walkthrough that I've prepared for you. So only deviations that I did was I only did trial 1 in all these. So when you are doing these experiments, you're going to be using the average volume instead of on a trial by trial basis. I didn't want to calculate the average because, again, that would just be me doing the lab for you. I just wanted to show you a very similar example. So find the average volume, which is find these volumes, take the average, use that to do the process that we just described here, and then you're all done. And you just go through the questions as written. The last few questions, which are these analysis questions at the end, are just extra problems for you to try. You are probably already able to answer most of these. Number 20 is entirely about what sig figs are. Think about sig figs versus the need for precision, and so on and so forth. 21 is just a titration with, here's a volume, here is a number of moles. You do need to have a balanced equation to make this one work, but if you have read through the documentation, you should be able to write the balanced equation for sodium hydroxide and phosphoric acid. And then that's it. All right, so that's all I have prepared. There's 10 minutes left. The intent of Wednesday, of course, is to have a review session for any other questions that come up. So if you have any questions at this point, please go ahead and type them in the chat. I'm going to go use the restroom real quick, and I will check back within like 3 or 4 minutes, and I'll be happy to answer any questions at that time. So be right back. All right, I'm back, and it looks like a workbook. I almost opened the wrong thing. So workbook. I have to find the workbook. So let me get this off the screen real quick. So 5, 7, and 9. Let me see if I can do one of those. All right, so I have problem number 5 here. Now, unfortunately, all I have is the key, so it's just going to show the whole thing here. So I could do this first one. I think this will be the only one that we really have time for. Let me just hide that. We'll go over the process here. All right. So Samita loves her funky units, and Samita was the one who made this book. So there's a bunch of just like random stuff. Because nobody works in gallons, right? Nobody gives a shit about gallons. So we have sodium bicarbonate here. And I want to find the weight of solute in 0.750 gallons of a 1.50 molar sodium bicarbonate solution. So what that means is I want to know the solid part. I want to know how much sodium bicarbonate is in here. Well, if I know molarity and I know volume, I know moles, right? And if I know the number of moles, I can figure the mass out. And I can figure out whatever unit I need that to be in. So this question is asking for pounds. So let's do that. So the molarity is 0.750 moles of sodium bicarbonate per liter. And the volume is 0.750 gallons. Which those don't cancel, right? So what I need to do is I need to get this to be liters. So we need to go look up the conversion for gallons to liters on Google. So 1 gallon to liters. So in 1 gallon, there are 4.546 liters. Oh, wait, hold on. That's not right. This is the US gallon bullshit again. Google does not automatically default to US liquid gallon. That's right. There we go. So that's how many liters are in a gallon. Make sure you're using US liquid gallons. This is another reason why nobody uses a gallon, is because there is that discrepancy. Nobody knows which gallon to use. Like, there's even an imperial gallon. Oh, which is what that is. We're not British, so we don't use that gallon. So these units will cancel out. And, oh, I just realized I used the wrong... this number is wrong right here. Right, where'd my problem go? Yeah, there we go. Okay. So how many moles are in this sample? 1.50, 0.750, 3.785. And so I got 4.26 moles of sodium bicarbonate. So that's how many moles were in the sample. And so now I can take that number and I can turn that into a mass. So moles of sodium bicarbonate, grams of sodium bicarbonate. How many grams are there per mole? Well, thankfully, Samita has already looked that up for us. there are 84.01 grams per mole. So this calculation, if I type this in my calculator, I would get 357.7 grams of sodium bicarbonate. But she wants the answer in pounds, so we have to turn grams of sodium bicarbonate into pounds. And according to Google, how many grams are there in a pound? Should be like 453.6, yeah. So 1 pound, 453.6 grams. And so that ends up being 0.788, 0.789 actually. There we go. And so that's what I got for the answer. And that should be what the answer is here. Yeah, that's what Samita got too. And it looks like she did it exactly the same way that I did, so. Now you'll notice that Samita uses all the digits. And the intent is that if you are doing all of this in one giant multiplication step, which you can, then you would be saving all those numbers anyway. If you chop it off to 3 sig figs like I did here, you'll notice that I still got the same answer at the end anyway. And even if mine was slightly different, it would be off in the last digit, and that digit's estimated anyway. So the short answer is it doesn't really matter if you keep all the digits or not, as long as you aren't rounding 75 times. Because every time you do that, and you don't keep the digits like I did, you do introduce a little bit of error. But generally speaking, if you only do that once or twice, the error that you're introducing is so small that it doesn't affect your answer in any way, as you can see here, because I got the same answer even though I rounded at that point. So don't worry about keeping all the digits if you don't want to. Some questions ask you to tell me the answer for an intermediary step anyway, and then you don't have that information carried forward anyway. So I just, as practice, I just do sig figs whenever I get to a spot where I might have to report something, and then I just keep those numbers as is going forward. All right. I unfortunately don't have time to do number 7 and 9 because the class is pretty much over now. But 7 looks to be very similar. It's just that your volume is going to be cubic centimeters. If you were curious what a cc is, it's a cubic centimeter. And so you're just going to figure out how many grams are in there. So that'd be this many grams. You turn into moles. You use the molarity to figure out what volume that is, and then turn that volume into cubic centimeters. And then for number 9, it's basically the same thing. So molarity times volume equals moles, but you need a volume that is not gallons. So turn that into liters. Multiply that volume by the molarity. That'll tell you the number of moles of sulfuric acid that you need, and then you can turn that into grams. And it looks like you get a giant number for your answer. So, are there classes next week? No, there are no classes next week. There's just final exams. However, on Tuesday, we will have a review session if students bring questions for me to do. So, if you still want me to go over these problems on Tuesday, I can definitely do it then because we'll have time. If you still want me to go over these problems later, you can also message me in the Discord. I have to take off for a little bit, but later tonight I can come back and do that. But yeah, no more classes at all. We'll have a review on Tuesday at the normal time. And then I believe the final exam is on Wednesday, if I remember correctly. Let me look that up real quick. So, oh, this is on the screen too, so there's the calendar. Yeah, final exam is Wednesday, because that one I think I have to match up with the final schedule if they tell me to. Yep. All right, so Friday is your exam. Wednesday is the final exam. There is a review session on Tuesday. Lab Worksheet number 5 is due on Tuesday. Last call will be Wednesday. Although, since that's your final, I'll probably extend it to Thursday. But yeah, that's really all I have. So I guess it is time to shut everything down. So, oops, that's the wrong screen. There we go. So I do want to thank everybody for coming out to the last lecture. And I don't really have anything prepared other than to just say thank you. So thanks for everything. I hope that at the end of this, all the crazy shenanigans and crap that we went through, and for as challenging and difficult as a lot of the work was in this class, I hope you got something out of it, and I hope that you enjoyed it. And I hope that you learned something about, well, how to apply it to the world, because the world is a crazy place. And the more you know, the better you can react to it. So, thanks again. Time to shut it all down. Have a good night.